Hello, so welcome to my video series on neural networks from first principles. I'm hoping to just make this a three-part series. So the first part will be covering what a neural network is, so you'll be able to understand exactly what you're looking at, the so-called forward paths of the network, and I'm going to be covering some linear algebra prerequisites that you're going to need to know as well. And the second part of the video series, I think, will cover the calculus prerequisites that you're going to need to know and the so-called back propagation algorithm, right? And we're going to power that with gradient descent. You don't have to understand what all that jargon even means. We'll get to that in the second video. And I suppose the third video will just be, maybe we'll use Python. I feel like Python is just so widely used now that, yeah, we'll just use Python or NumPy or something and we'll code out some simple neural network. I'm thinking maybe just a classic XOR function or something of the sort, right? So let's start with the prerequisite linear algebra, because I feel like if you don't have that, you can't really do much. So let's draw a Cartesian plane. I don't know why it's so thick. Oh, it's 6, that's why. Okay, it's really, really thick. And we'll just say, let's say this is 1, here like this, 2, so make this a, oh no, let's make this a little bit larger, this 3, so it's not the best, but I'm hoping it's enough. Let me choose something that's like not as thick. Suppose we had a vector, right, like this. Can I use arrows? Yes, they do have arrows. So a vector, I hope maybe if you did like high school calculus, you'll be familiar with a vector as something that has magnitude and direction, right? You can think of it as some value on the Cartesian plane, right? And so normally if you wanted to write a value here on the Cartesian plane, you would just put 1, 1 in brackets, right? Like so. You would just put 1, 1, but that's just not how you would represent a vector. So you can represent it typically with an x, right? And just put any variable you want. We'll just call this vector x. And you put an arrow over it to sort of indicate the direction aspect of it, magnitude and direction, right? And so this vector would be encoded like this. Okay, this 1, 1. And you might be familiar, this is like a matrix in a sense, right? So hopefully you have some inkling now of what a vector is. Now, suppose then we had a second vector. I'll take this one. And oh no, I need to switch back to shapes, right? And our second vector came like so. And we can call this vector y. And we'll say the vector is at position 2, 1. How would we add these two vectors together? Well, it's quite simple. So x plus, I think I should come more to the right. So x plus y, like this, would just be 1, 1 plus 2, 1, right? Fairly straightforward so far. And you just add the components across. So 1 plus 2 is 3, and 1 plus 1 is 2. So your result vector will be at position 3, 2. Now there's a geometric interpretation to this as well, and it's taking the tail of your second vector here in green and sticking it onto the head of your first vector in red, and that will give you the resultant vector. Now I'm hoping it's going to allow me to select, I'm not sure if I can. Let's see. Oh no, not all strokes. Okay, it's not allowing me to do what I wanted to do. Let me see if I can just like, oh no, yeah, it's moving the entire thing, which is what I do not want. Oh, nice. So I got to select this single vector. Lovely. So if we took this vector, right, and sort of stuck it onto the head of this vector here, the result, right, is at 3, 2. Well, I didn't put in the third part in the Cartesian. Oh, whoopsie daisy. Let me go back here. And let's just put in 3 here, right? And so this is exactly what vector addition means geometrically. Now let's talk about vector multiplication, which is, I think, the most important part. Now, before I go over to vector multiplication, I sort of want to give you a better idea of what a matrix is, right? Now, I'm actually just going to send you to Gilbert Strang again, MIT's 1806. Please take that course. That is like one of the best courses you could take for linear algebra. I feel like it's so good. Anyways, so assuming again that you don't know what a matrix is, then I'm at least hoping that you know what systems of linear equations are. Now suppose we had x plus y plus z like this is equal to 1, and we had, I don't know, 2x plus z is equal to 2, and then just x plus y plus 3z is equal to 4, like so. Now, you might be familiar from high school math, you would solve this like with substitution or with elimination or however you wanted to do it. But the idea is a matrix, right, can be, this system of linear equations can be represented using a matrix, and it's called the matrix of coefficients. Now, here's what it looks like. I'll switch to blue. What you do is you take the coefficients of each equation and you encode it into matrix as follows. So x, its coefficient is just 1, right? There's a 1 sitting in front of this x. So it's 1, 1, 1 for the first row. So each row of the matrix is corresponding to an entire equation, right? And for the second one, it'll just be 2. There's no component for y, so it's 0, okay? 1. And then it's just 1, 1, and 3. So, okay, so fairly straightforward. Now there's 3 vectors that we're working with here, x, y, and z, 3 unknowns. And so you encode that like this, x, y, z. Right, and this is precisely this vector that we were looking at up here, right? Now, and this is a matrix multiplication. Now I have to tell you what matrix multiplication is, and I'll do this to sort of like convince you, right? And so this result will be this right-hand side vector 1, 2, and 4, 1, 2, 4. So this is known as AX equals B. Oh, there's some cats outside, actually. I'll check them out in a bit. Some kittens. Okay. How do we carry out this matrix multiplication? Oh no. I'm going to show you, right, so normally they will teach you like dot product or something like that. I'm just going to show you a linear combination of columns, and the dot product, so-called dot product, will show up anyways. And what you do is you take the first entry of your vector here, x, right, and you multiply it by the first column of your matrix. So it's going to look like this, x multiplied by 1, 2, 1. Plus, now you're adding, and I hope you remember what vector addition means geometrically, right? And then you take the y, right, and you multiply it by the second column of your matrix, like so. 1, 0, 1. And you take z, and you multiply it by the third column of your matrix, so you get 1, 1, and 3, right? So it's fairly straightforward, but I hope this is what's called a linear combination of columns. Can you see? Okay, let me see. And this is equal to 1, 2, 4. Essentially, what this problem is asking you, right, is what exact linear combination of these 3 vectors will produce, right, our resultant vector? And I hope you remember what vector addition really is. That's what we mean by linear combination. We're taking vector addition, right? So some amount of x, some amount of y. Oh, sorry, z is supposed to be here. Forgot the z. Whoopsie daisy. Some amount of z, right, will produce this resultant vector. And that's what you're doing when you're trying to solve the system of linear equations. You're looking for the exact coefficients, right, that comes in front of each of these vectors, right? And when you add them together, you will get this resultant vector here on the right-hand side. Now, I'm not going to show you how to solve this. You can take a linear algebra course if you wanted to, but that's not a prerequisite of what we need to know. We need to know what matrix multiplication is. So we're going to carry this out, right? So this will just give us x, 2x, and x again, right? Plus y, that's 0, 0, y, and then z, z, and 3, right? So z, z, and 3z, like this. And then if we added them together, we're going to get x plus y plus z, right? 2x plus z, and we'll get x plus y plus 3z, right? One big vector like this, right? And this, right, is equal to 1, 2, 4. And you should notice that this structure here is precisely what we had up here. So that was just to convince you that a matrix really is just a way to encode systems of linear equations, right? Okay, and so I hope you understand the main premise behind matrix multiplication, because that's what we're going to be using. So let's go. Oh, God, I don't know why that keeps happening. Oh, it's because my touchpad's enabled. Let me disable the touchpad. Great. So that shouldn't be happening anymore. Now let's talk about the neural network. So I'm just going to throw you into the deep end of the pool and talk about this vector called x, right? This is just some vector. Remember, we already defined what a vector is, and it's called a feature vector, right? So it's what's known as a feature, okay? And if you look at the first layer of this network, ignore everything else you're seeing right now. Just focus with me on the first 3 nodes in this network, right? It's corresponding to this feature vector, right? So this vector x is just coming in here, right? What is a feature though? This is what you need to understand. Features are parameters, right, that are important to a problem we're trying to solve. So an example would be, I like using this example. If you're a real estate agent, right, and you had to sort of write a model or train a neural network that would predict what the price of your house is, right? What are some features or important things about the house that would enable you to give a prediction on the price? And that's the feature, right? So important parameters about a problem domain to solve. So for example, so with the house, I suppose we would say, does it have a pool? You know, how many bedrooms? Let's say number of bedrooms, so on and so forth, right? And you would encode that, let me come back here. You would encode that into your feature vector, something like this. So we can say, we can use a Boolean value, right? For the first input value here, say, okay, no, it doesn't have a pool. Number of bedrooms, we can use an integer 5. And so any number of parameters you think relevant to the price of a house, right? What's the crime statistic in the neighborhood, right? Maybe we can use something, right? Some kind of range value or something of the sort, or even like some probability from 0 to 1 or something like that to give the network an indication of that. So we'll say maybe 0.7 for it's like in a high crime rate area or something like that, right? Something to that effect is what you would use. So these are the features of your model. Now, this portion here at the bottom is the most important part of your neural network. And this is a so-called, so let me highlight it for you in blue. This portion here is what's called the hidden layer, right? And so these 3 neurons you're looking at here, everything about these neurons is contained inside of this equation. Now, it probably looks like a lot to you at first, right? But I'm going to try and break it down for you now. So what is this matrix W? So we're going to take it a little bit at a time, and then hopefully the picture will become clearer to you. This matrix W is what's called a matrix of weights, right? I'll explain to you what a weight is in a second, but it's going to look something like this. Let's say these are just like values inside of this matrix, right? It's called the weight. Now, the X, as we already said, is our feature vector, right? So it's going to look like this. So this is a matrix multiplication, right? And you already know how to do this matrix multiplication. I'll just remind you very quickly. First value here will come and multiply this first column here. Second value here will come and multiply this column here. And third value here will come and multiply this column here. Great. Now, then you see some plus b, right? So what is that? That's what's called a bias term. We're going to ignore that for a second, right? But it's just some vector, right? Well, I should put the vector sign over it. But it's just some other vector that we're adding. It's called a bias. And I'll explain what that is in a second. Now, let's go back to this weight matrix and sort of demystify what it is, right, in relation to this network diagram. So every row inside of this matrix, I have a different color I can use, maybe this one here. Every row inside of this matrix is corresponding to a single node in the hidden layer. Remember, the entire weight matrix represents the hidden layer, right? But every node inside of this weight matrix is represented, every node inside of your network is represented by a row in your weight matrix. So this first row will correspond to, let's say, this node here, right? This second row here will correspond to this node here, and so on and so forth, okay? Now, there's something very important that you need to understand about matrix multiplication, and it's that your shapes need to match. For instance, right, let me give you an example. If I wanted to multiply these two vectors, 1, 1, right, times 1, 1. Question is, could I carry out this matrix multiplication? Let's try to do it logically from what we've learned, right? I'm not here to teach you rules. I'm here to teach you how to reason about for yourself from first principles. So again, by what we've been learning, we'll take the first vector, right, or the first input into this vector, and we'll multiply it by the first column, right? And then we'll take the second input of the vector and multiply it by the second column. But you say, wait a second, there's no second column here. And so exactly, this matrix multiplication cannot happen, and it's invalid. And so the rule they would teach you, which I've never memorized, but somehow I'll remember because this is the way in which I look at matrix multiplication. The rule would be, what is the shape of this first matrix here, right? It's 2 rows, right? 2 rows by 1 column. And it's multiplying, what is it multiplying though? Right? It's multiplying 2 rows again by 1 column. The problem is the geometry doesn't match. This inner product here needs to match for you to have a valid matrix multiplication. If the inner product does not match, you cannot do the matrix multiplication. And so the constraint, right? The constraint really is this input vector here. All right? That is always your constraint, especially in the context of a neural network. And so if you look here, our input network or input vector, right, into the network has 3 components, right? What does that mean? What does that tell us about this weight matrix? If we only had, right, the input vector, so let's come over here to the side for a second. If we only had this input vector here with 3 components, how would we go about constructing a hidden layer, right? What's the first thing that we need to do? Well, obviously, we need to give it 3 columns, right? Otherwise, so it needs to have, okay, great. So it needs to have 3 columns like this, right? Otherwise, you will not be able to take linear combinations of those columns correctly, right? The geometry would not match. So is this a valid matrix multiplication? Yes, it is, right? So this is, what is this? 1 row by 3 columns times 3 by 1. Okay, so, and your resultant would be 1 by 1. This is actually what's called dot product, right? So, okay, and this is how they normally teach you matrix multiplication, but you don't see it like this as a linear combination of columns. So you can actually derive the dot product from this linear combinations of columns. That's why I didn't bother teaching it to you in the first place, because to me, right, that is dot product as they show it is just something that some formula that you memorize, right? I have to try to remember. No, do not do that. Try to come up with a system. I'm not telling you have to use my system or use Gilbert-Strang's system, but you come up with some system for yourself that would allow you to reason about these problems for yourself without having to memorize like a set of, obviously you've got a set of axioms, a set of like core principles that you follow, right? I'm sharing my core principles with you, or Gilbert-Strang's core principles with you, but by all means, if there are better ones out there, feel free to enlighten me as well. Thank you. Okay, so I got beside myself there, but I've already said that the first row will correspond to a single neuron, right? And we saw in our network here that we had 3 neurons, so we know we can have 3 rows like this, but there was actually no reason that we needed to stop at 3 neurons. We could have 1 billion neurons. The important thing, right, is that we have the 3 columns here. Okay, that's the important thing. All right, now a little more about this weight matrix. You might be like, where does it even come from, right? Initially, at the start of the network, the weight and the bias is randomized, right? It's just randomized. And then your network will learn and adjust those weights and biases, but we'll get to that later on. So you understand, right, how to carry out this matrix multiplication now. Why is it that we're adding some bias term, right? This is what's called a linear transformation. This portion here, right, is called a linear transformation. But when we add this bias term here, this other vector, it's now what's called an affine transformation or non-linear transformation. But I feel like the word non-linear is a little bit misleading here because it's still linear, quote unquote linear, in the sense that if I wanted to give you like a very like naive example, suppose we had a plane, right, like this, and we sort of so we had a plane right? And the plane was sort of described by, I don't know, some two basis vectors. Let's say we had some vector like this and some vector like this, and all linear combination of those two vectors would describe a plane, right? What happens is that when we shift, right, this by some b term here, now we're not up by a single plane. It's what's called a hyperplane, because once you have multiple of these basis vectors, you get what's called a hyperplane, right? And that's when you're up into, like, I don't know, 900 bajillion dimensions, right? And that's what linear algebra is really, really good at, though, because you can look at small cases and then it generalizes. But all right, this plus b term, right, all you're doing is you're shifting the hyperplane. You're shifting this plane away from the origin. Right now, right, it's sort of stuck or centered at the origin. But when you add b, you translate it somewhere else, right? So that's all b is doing. But it's a very important term, and it gives a bit of non-linearity, quote-unquote non-linearity, but it's still linear in the sense that the main portion is a linear transformation, right? But as you'll see later on, and I don't want to get into that right now, so let me just stick to the main themes of things and not get too out of hand with it. Okay, so you understand, right, what the input layer is, and hopefully you understand what this hidden layer is, right? This hidden layer is just this wx plus b part, right? And p, what you get when you carry out this is what's called a pre-activation, right? That's why I called it p. It's called pre-activation. And then what you need to do is take a function called ReLU, right, and apply it to that vector p that you get. So you carry out the matrix multiplication, right? You get a linear transformation. You add b, so now it's an affine transformation, or a quote-unquote non-linear transformation, right? But the reason I don't like to use the term non-linear transformation, because I already explained. In a sense, it's still linear, right? All you've done is shifted it away from the origin. That's all you've done, right? So okay, but I hope the idea is coming across. I don't want you to get bogged down with jargon or language. I hope the idea is coming across. So you carry out this computation here, right? And you're going to get some vector p. And I hope you can see what the shape of p is as well. I'm not going to spell it out to you, but take some time to... It's actually right here. Okay. I hope you might have, been able to guess what the shape of p is. And so what is ReLU? ReLU is a function... looks like. So these are some of the activation functions you can commonly use, and we're not going to go through most of them. I'm just going to show you what sigmoid is and what ReLU is, and the others you can use or go over later on. So if you look at ReLU, right, so how you carry out this function, again, it's just the same as if you were doing multiplication, right? Remember when we were taking linear combinations of columns up here, where is it? Here, right, we had an x and it was distributing into every component inside of this vector. Well, you're doing very much the same thing here. You're distributing ReLU into every single component here. And what ReLU is going to do, right, is if the function is defined here, right, if the value is positive, right, nothing happens. It just passes through just like this. However, if the value is negative, like you can see here, the second component is -1, it's going to squash it down to 0, right? And then again, 0.2 is just barely positive, just lets it pass through. Now this activation function here is what introduces the true nonlinearity, right, into the network. Okay, if we did not have this activation function, and all we did was we stacked a bunch of these networks together like this, hidden layers together. At the very end, right, all we would have is just a linear transformation, or, well, an affine transformation, right? Because it's just borrowing information from what came before it, and there was no way. It's still linear in the sense that I was trying to explain to you, right? Yes, the hyperplane is shifted away from the origin, but it's still a hyperplane, right, is what I'm trying to say. Okay, now, how should I explain from here? Now, I suppose we should go through an example, right, with the network, and take it from there. So let's suppose, right, like, what does this look like? Let me just draw a little box here in the corner. But I feel like already you have a very strong understanding now of what's happening, right? Oh, so we covered the input layer, we covered a hidden layer here, but you saw, like, there's another hidden layer over here. Like, what is this about? All this is doing, right, is taking this, and this, right, and it's using it as the new input value, right, of the next hidden layer. And so I think I'll show you what that abstraction looks like algebraically, and then you'll be able to see it in the diagram as well. Now, so we'll say W, right, so we'll say Wx plus B, right? And we already said that this corresponds to a single hidden layer, right? And this is your initial input layer, right, or the input vector into your matrix W, right? And then we're going to apply ReLU, right, to whatever output we got here, right? So we said this was like P for pre-activation, right? And then we'll say ReLU of P. Let me be very specific with my notation. ReLU of P, right, is equal to A. We'll just call it A for activation or something, right? Great. Now, how would we go about nesting this together, right? So far in the network, we're here, right? We're here now at the first layer. The first layer is finished computing, and we want to feed this, right, into the second layer. Now, the second layer of your hidden network will look like this. Oh no, I keep selecting the wrong black marker. In fact, let me use the blue. I feel like I like the blue a little better. So the second hidden layer will look like this. W2 times your A, like this, plus B2. Now I need you to notice, and we'll just call this P2, like this, for pre-activation. Now I want you to notice something very subtle. Notice this W2 is different from this W up here. This means, right, that every hidden layer inside of your network has its own weights, right? And notice the B is also different. So every layer has its own weights and it has its own biases, right? So that's very important distinction to note. And then the input vector into this W matrix is A, right? And remember we said before that the W matrix is sort of dependent on this input vector. The shapes have to match, right? So if we look here very carefully, this input vector here, or this hidden layer, has 3 neurons inside of it, right? That means, right, that our W matrix needs to have 3 columns inside of it, right? And yeah, but of course you can arbitrarily pick how many nodes you wanted to pick, or how many neurons you want inside of that layer. Here I chose 3 again, but you could have chosen, I don't know, 100 of them. So imagine, right, so take this exercise. Imagine, right, that this layer here had 100 neurons inside of it, right? And then it was feeding into another hidden layer. Can you think to yourself, like, how many columns will the weight matrix of the next layer need to have, right? Just, you know, maybe put it in a comment section or something. So, and you know, that'll sort of help you test if you actually understand what's happening. Okay, so this will give us the second pre-activation, but remember, we're not done, right? We still have to call ReLU or call an activation function on this. So we'll use ReLU again. So we'll call ReLU on P2, like so, right? And this will give us we'll just call it A2, right? So our second activation value. And so now we're here in the network. So bad news, the recording cut out. Good news, you didn't miss a lot. So let me try to get you back up to speed. So we stopped off at the last hidden layer, right? So next thing we have to compute is just the final output layer. And so we just did a little bit of math here. It's more or less just the same thing. So it's this, we need another weight matrix, right? We're going to use the previous computed activation from the hidden neuron as the input into that weight matrix, right? We're going to add a bias. And so finally, though, we're not going to be using ReLU. We're going to be using something called sigmoid. And I made a point to, like, have you think, right? Look very carefully that this output neuron is one single neuron, right? And so I wanted you to think about what the weight matrix was going to look like for this, right? And we said, well, okay, that matrix is going to be 1 by 3, right? It needed to have 3 columns because the previous layer before it, right, is feeding in, right, three values, like a value in R3, right? So that vector has 3 components. So, and we already been over this, like the geometry has to match. And I was saying, like, the outer product also tells you what you're going to get, right, as your result of this multiplication. And we're going to get a scalar, a single value in R1, right? And so I was also raising the point that your bias term that you're adding, the geometry needs to match what this output value is going to be, right? I cannot add a value, for instance, in R2, like this, a vector in R2, to a scalar like this. This will not work, right? Because remember, we were doing component-wise addition. There's nothing defined up here. So that simply will not do. And so I was also raising the point that for all the other biases and all the other hidden layers, the geometry has to match, right? So hopefully you sort of see what's going on there. And then I was saying, okay, well, you're going to get some scalar value from this final output layer, right? And we're going to do is apply this sigmoid activation function to it. And what sigmoid is going to do, let's say we had a value like, I don't know, 100 or something. Sigmoid is going to squash it down into a probability value. So it's going to be squashed between 0 and 1. So maybe it'll be like 0.7, right? And when what's going to happen is it's going to use the objective function, the cost function, loss function, whatever you want to call it, and it's going to compare against what the expected value is from the training data set, right? And it's going to say, hey, wait a minute, there's some problem here. And it's going to, okay, we're going to use back propagation and gradient descent, right, to figure out how is it we're going to adjust the weights and biases inside of the neural network, inside of the hidden layers, right? How do we tweak those weights and biases such that this output vector, right, or this output value nudges a little bit closer to what the expected value is? And that's really all training is going to do. It's going to do this over and over and over again until we converge, right, to the correct value. Okay, and that's how your network is going to be able to give you accurate predictions. So it's really just one big mathematical function, really. So, okay, and that's pretty much everything you need to know about the forward pass, right? For the second part of the video, I'm just going to go over the prerequisites that you'll need to know for calculus. So you'll need to know limits. You'll need to know, well, we're not going to go for that, really. We're not going to do, don't worry, it's not going to be epsilon delta definition of the limit. We're just going to go over the basic, maybe the fundamental theorem of calculus, right? The derivative. You're going to need to know the chain rule. So go over that. You'll need to know what a partial derivative is. Maybe you'll need to know what the Jacobian is, but once you see what the partial derivative is, you'll just understand that it's just a matrix of partial derivatives. And that's fine. And I think, yeah, that should be the crux of what you'll need. And then we'll just try to do a full concrete example from start to finish. So we'll go through what happens, right? We'll get actual numbers in here now, right? And we'll use the XOR example. So here, this is what XOR, this is what I was trying to explain earlier as well. So I thought this was a perfect example, right? Forget about this for now. So XOR will look something like this, and I hope you know what XOR is. It's just a function in digital logic. It's a gate, right? It's a logic gate. And what happens is that if both the inputs are on, the output is 0. Otherwise, though, if a single input is on, right, then the output will pass through, and if both of them are off, then the output will get 0, right? So the cases that this gate is off is 0, 0 like this, and 1, 1 like this, and it's on for all other cases, right? So that's what your XOR gate is going to look like. And so if you were to try to like plot it like this, it looks something like this, right? Now, remember early on in the video, I was trying to explain to you this idea of what a linear transformation is, right? It's something going through the origin like this, right? And like if you were trying to use like linear regression or something to try and fit this, try and find a best fit line, there's no way to use a line to separate these four parameters from each other, right? We cannot classify them, right? Can you see that? We cannot classify them. There's no way that I can rotate this thing around the origin to get it to separate. And this was WX part I was telling you about. And then we added a bias, right? And there's actually some history to this as well. And maybe I'll take some time later on to go over the history of where it actually all came from. And that's actually the true first principles thinking. But okay, we only have so much time, you know, live so long. But okay, what I was trying to tell you about the bias is all you're doing is you're shifting the hyperplane, right? So let me just erase all of this. So now instead of it being on the origin, it's an affine transformation. So it could look something like this, right? But again, you can see there's no way that I can put this thing to have it to properly classify, right? So that's where we have this activation function. The activation function allows us to bend or kink, right? So now it's no longer linear, it's non-linear. We can approximate any polynomial, right? And so you can see what it looks like over here in 3D, right? So we kind of have something that comes up like this and it kind of bends over like this and then comes over like this. And now we can classify them properly, right? So we can say, okay, well, this belongs to this boundary and these two belong to this boundary here. So, and that would be what the sigmoid and the polynomial transform is going to do. Okay, but that's all just jargon. I hope at least you understood the idea that I was trying to get across. Okay, so I feel like this went on for much longer than I was hoping it to go on for, but hopefully you learned something. So thanks for watching.